Okay, good morning. We've been discussing op-amp design, right? And we saw that we can improve the op-amp by using a current to voltage converter to convert the output of the GM into a voltage. And that leads us to many different op-amp topologies, which are basically progressively better. That is, by using, you make a better op-amp and use that in this feedback loop to make the current to voltage converter, you get better and better op-amps. And this is basically a set of op-amps which have this nested feedback loops. Okay, so these are called Miller compensated or nested Miller compensated op-amps, depending on how many loops you have. Okay, so the first step, the first improvement gives you this classic what is called the Miller compensated op-amp. So let's say this is what we are trying to build. In this case, the loop gain is A of S by K. And the two-stage op-amp that we have has this is our two-stage op-amp, right? So we have this C and C1 and C2, which could include the load capacitor also. Okay. So now the zeroth order or first order calculations that we did says that the unity gain frequency of the inner op-amp, which is GM2 by C2, must be greater than the unity gain frequency that you are trying to realize, GM1 by C. Okay. Now, of course, this is the unity gain frequency of the op-amp. This is the unity gain frequency of the inner op-amp. Okay. Now, like I already said, we many times when you are analyzing only the op-amp, we talk about the unity gain frequency of the op-amp, but that itself is not relevant. What is relevant is the unity loop gain frequency. So you have to implicitly assume that whenever I talk about it, I'm talking about putting this op-amp in unity feedback. Okay, because the unity gain frequency of a open loop system is not quite relevant. I mean, certainly not for stability, right? So now, if we instead use the unity gain frequency of this feedback loop, it will be GM1 by K times C. Okay, so that is the unity loop gain frequency of the inner loop must be greater than this, right? So this is essentially this is something that you know in any dominant pole compensated system. What is a dominant pole system? What is a dominant pole system? So basically the loop gain has a predominantly first order behavior before the unity loop gain frequency. That's what is meant by a dominant pole system, right? So you just have one pole before the unity loop gain frequency and all the other non-dominant poles and zeros happen afterwards. So before the unity loop gain frequency, you only see like 20 dB per decade slope. And of course, at some point, the DC gain will not go all the way to infinity. It will flatten out at some value. Okay. Whereas there are other systems also, as we'll see. So in such cases, I mean, we know that all the non-dominant poles and zeros must be beyond the unity loop gain frequency, and this statement is essentially saying the same thing. But of course, intuitively, we got this idea that the inner op-amp must be operational over the frequency range where you want the outer op-amp to be operational. Obviously, it should be beyond that. Now, just a rehash of or a recap of some results that you already know. This one, you know that from earlier courses, with C equal to 0, that's not an op-amp, or that's not, that's just a cascade of two stages, right? If you have this C equal to 0, you can think of it as two common source amplifiers, one after another. Okay. So then there were two poles. One was at RO1 C1 and the other one was at RO2 C2. Now, if you have a significant value of C, we know that the first pole is approximately at, what was it? So the capacitance is still C1, or capacitance is C1 plus Miller multiplied C times 1 plus GM2 RO2, and the resistance is still RO1. Okay. So this is easy to see that essentially you have this capacitor being multiplied by the gain of the second stage, DC gain of the second stage. Okay. And as far as the other one is concerned, now because of feedback, the resistive part also changes. Okay. So firstly, we have right. So now if you apply a test voltage here, this, what is the kind of current that will be drawn? One is of course just the series capacitance. The series combination draws a current which is Vx times S C1 by C plus C1. Okay. So you have an effective capacitance that is equal to so much, right? But additionally, you have a current through this GM. Okay. How much is that? That will be Vx times GM2 C by C plus C1. Okay. What does that mean? This whole thing is basically a conductance. Okay. And this conductance appears because of feedback around the second stage, right? So this P2 is basically related to the total conductance at the second stage output, which consists of GM2 C by C plus C1, plus of course you also have 1 by RO2, which is already there to begin with, right? And then the total capacitance at the output of the which appears at the output node, which is what? You have C2 right there, and then you have the series combination of, right? So if you write out the transfer function for this, you will get some function of this form. Okay. And then you do whatever approximations to find the poles. That is, what are the approximations you make for if you, obviously you can try to solve the quadratic exactly, but you can't make out anything from those expressions. So what, how do you approximately find the roots of a quadratic if you know that the roots are far apart? What is the approximation you make? What's that? So you assume that with When S is substituted by one of the poles, the higher pole, only these two terms are dominant over the other one. And when it is substituted by the lower value, these two are dominant and the other one is not dominant. Okay. So with that, you will get the low frequency pole to be approximately what? Minus 1 by A1. Okay. Our notation itself is this. Pole is at minus P1 and then okay. So if you do that, basically this is what you get, but you should have an intuitive picture of why these values come about. Okay. So you have some resistance and you have some capacitance associated with which give you these poles, and this is what it is. Okay. So now what was the, how is this related to the condition we had? We wanted the non-dominant pole to be greater than the unity loop gain frequency. Okay. Now, if you look at this non-dominant pole, this looks more complicated than what we have earlier. But if you have C1 equal to 0, right? So if you, which is our earlier case anyway, P2 with C1 equal to 0 is approximately GM2 by C2. Okay. This is the unity gain frequency of the inner op-amp if C1 equals to 0. Okay. If C1 is not 0, it will change. That's why you have all those modifications. So what I'm trying to say is whatever we got intuitively, which is this, does make sense. Okay. It's not precise because we have left out some details when doing that. But at least you get the idea that essentially if you make this nested type of op-amp, the further GMs, GM2 tends to be higher than GM1 and GM3 has to be higher than GM2 and so on. Is this okay? So again, I won't go into how we derived all this, these things you have done earlier, right? But it's basically saying the same thing that if you take this new picture where you're doing this current to voltage conversion using the second stage using GM2, then that op-amp has to have a unity loop gain frequency beyond the unity loop gain frequency that you're trying to realize. Okay. Any questions about this nested op-amps and so on? Any further details, you can do this by simulation. Okay. Because as you can see, there are a number of parasitic elements here. And the more stages you go to, the more poles you will have and so on. So finally, you will have to adjust all these values so that you get good enough stability margins, and that you do by simulation. Okay. Any questions about this type of op-amp? And you can keep on doing. So that is, you can go to, there are first of all some circuit enhancements even in the two-stage op-amp, and then you can go to 3 stages and so on. But anyway, if you have to design a 3-stage op-amp, you should be able to do it. Maybe with some trial and error for the values. Okay. If you look at the next assignment, I think it has op-amp design with the control sources first, right? Okay. Any questions about this? We'll see. The transistor level implementation we'll come to later. But the bottom line is, if you now are able to, so that's why we have divided this into, we first look at everything at the control source level. Now, if you are able to implement the control sources using transistors, you can implement any of these loops. Okay. If you understand it at this level, then first of all, there may be a variety of choices for how you realize GM1, GM2 and so on. Okay. And of course, every circuit comes with its opposite polarity counterpart. Whatever you can do with NMOS, you can do with PMOS and so on. So the number of transistor level circuits can be a lot. But if you understand it at this level, when you see the transistor level circuit, you should be able to sort of mentally classify it into one of these things and then see what's really going on. Okay. As we already said, the first stage is this GM1, it tends to be a differential pair because you have to have you want to have a difference input, okay, in the general case and so on. Any questions? Okay, so now our basic op amp was just this. I'll show the buffer, and it has, I'll show the output resistance also explicitly, RO1. See, okay. And we can, for instance, put this in unity feedback, okay. So this is a unity follower. And as we already repeated several times, the output voltage, which also has to be appearing here, that causes the current to flow through this, and that has to come out of GM1, right? That's why you have to have a difference voltage between the input terminals of GM1. That's what gives you this imperfect virtual short, right? The two voltages should have been the same, but they are not the same because GM has to drive out some current. Okay. Now we had one particular fix for the problem. That is, instead of just pushing the current into this impedance to develop a voltage, we made a proper current controlled voltage source. A current controlled voltage source gives a low input impedance. So this output voltage doesn't appear across RO1. So that was the idea behind the previous set of improved op amps that we realized, right? So what else can we do to prevent this problem? That is, the main point is, if there is some current coming out of GM1, you will definitely have some difference voltage. I mean, in fact, the difference voltage is the cause, the output current of the GM is the effect. Okay. If GM has to put out some current, it has to have a difference input voltage. Okay. And that's what has to be prevented. What else can we do to prevent that? Okay, we had one solution, but we may want more than one. What else is a possibility? That we already done, right? So, okay, maybe we had two solutions, we want a third one. Huh? Pass the current through RO1 from where? So, okay, now basically the point is that some current is flowing there. Okay. So now, let's say I connect some current source like that. And if I adjust that Ix to be exactly equal to the current through RO1, then what happens? What will be the current? This is steady state, right? So let's again assume a DC VI, and first I let it reach steady state. Okay, then what I find is that some current is flowing through RO1. VO output is a DC, some current is flowing through RO1. So now I realize that, okay, I can supply that current from outside, possibly. And if I make this Ix exactly equal to the current from RO1, what will happen? What happens? What is the current coming out of GM1 in that case? 0. Okay, so what will be the input voltage of GM? Also 0. Okay. So now, of course, I don't know how much current I have to pump in, right? Because I would be using this for any value of input, so VO will vary. And RO1 itself is not as though I know its value accurately. It depends on the transistors and bias point and so on. Okay. So now, essentially, somehow I have to vary Ix. Okay. So that it matches the value of RO1. So what should I do? So one more, I already told you, answers to most of my questions is this. So, so now I have to continuously adjust Ix such that what happens? Yeah. R is not accessible, right? It's not a separate resistor. It's just inherent property of the transconductance. You don't want to make VO 0. I mean, VO should be controlled by VI, right? Then you will kill the circuit. Okay. So now again the problem is we continuously adjust Ix until what happens? Yeah, how do I know it matches the current? What should I look for? What is something that I can look for? Yeah? What is it? I mean, you need to increase the gain. I can't hear anything you're saying. Difference of the current. Okay. So what do I sense? See, the thing is I have to be able to sense some error, and based on that I have to continuously adjust Ix. So what is the quantity that I should sense? So first I let it reach steady state, let's say without Ix, and then some current is flowing. Now I connect that current source Ix, and I'm going to change it continuously until something happens. I mean, but what should I look for? I have to be able to look for something, right? I cannot measure the current in RO1. That's not something that's separately available. Okay. RO1 is just some property of this GM1. I cannot really separate it. So what is it that I should do? Huh? So basically, now, no. Okay, basically I think what you're suggesting comes out to increasing RO1. That is the cascode, right? Okay. So my goal is to make the output current of GM 0, right? I don't care how much current is going into RO1. I'm willing to supply that. Okay. So my goal is to make the output current of GM1 to be equal to 0. How do I sense that? That current is not easy to be sensed directly. So what should I do? I look at the input voltage. Okay, because I know that any current coming out of GM1 is only due to its input voltage. So what I'll do is I will look at this voltage, the error voltage VE. Okay. Adjust Ix continuously until VE goes to 0, or basically you adjust Ix in a way that reduces this VE. Okay, this VE itself is a measure of how much current is coming out of GM1, right? Is this okay? Okay, so this is the process that I want to happen, and I want to make it using circuits. So first of all, I need a variable current source. How do I get that? So I need a variable current source. So what should I use in its place? You mean I will, what do you want to do? No, the voltage across RO1 should still be VO, right? Current? Right. No, if you push a current, it will always go up. How do you find out whether, see, why? No, I mean, so first of all, again, let's imagine that Ix is 0, okay? The V naught will settle to some voltage, maybe not the voltage we want. Now let's say go on increasing the current. Now the voltage will go on increasing, that's all. How will you know when this is equal to that? Okay. So it's not as though when this is equal to that, this voltage stops changing. Even from this voltage was, let's say, 10% less than what it was supposed to be. If you go on injecting the current, it will go on increasing. That's all. Okay. So you can't find out here. What you want to make is that the error current coming out from GM to be equal to 0. Okay. So now first we want to make a variable current source. What's a reasonable way to do this? I mean, electrically variable current source. What is it? What is it? MOS, yeah. It's a voltage controlled current source, like one more GM, that's all, right? So now I'll have this, and if I vary this voltage, okay, so this is some sort of control. If I vary this voltage, the current will vary. Okay. And what is it that do I want? How should I vary that voltage? Based on what? Again, the process is outlined here, right? This is what I want to do. Okay. So how should I generate this control voltage? It should vary, the current should vary continuously based on VE. So, I mean, we have done this before, right? Yes. Connected to? No. That won't, right? I mean, if I connect it here, it will change based on VI. What I want is if VE is not 0, this current should go on increasing. Negative? Meaning basically you make the input of this equal to the input of that. Then that is just like adding GM, right? That's like changing the value of GM, that's all. Isn't it? If I just connect this in parallel with that, that's what you're suggesting. I'll connect these two inputs to those two. The two GMs will be in parallel. What I'll get will be a new value of GM. That doesn't fundamentally change anything. Okay. So the key is if V is non-zero, this control should be, or the current should be continuously changing in some direction. So what should I do? Op-amp. Okay. Op-amp meaning what is? I mean, what is the function? Error, what will you do with the error? If you want this continuous change, what should you do to the error? Integrate. So basically, you have to take this Vi and integrate it. This control voltage should be the integral of VE, sorry, not Vi, VE. Okay. So how do I do that? Like I said, an op-amp, and of course, what is op-amp we know at this point. Is that, right? So what happens now? Let's say again, you imagine that steady state has been reached without this extra apparatus. Okay. And this VE is positive. Okay. Now you connect this control voltage will go on increasing, which will go on increasing this current. As this current coming out of GM reduces. Okay. And when will it stop? When this control voltage is steady, which is basically when this voltage is 0. Right? Is that okay? So you take that error voltage, you integrate it, and based on that integral, you have another current source feeding to the output. Okay. So if this works ideally, then the whole process will stop when this voltage is steady, right? Again, for all these things, it's easiest to imagine a DC steady state, right? Vi is DC, Vo is DC. Okay. Finally, everywhere you should have DC. So now, if this V is not 0, the control will be going up or down. Things will still be changing. Things will stop changing only when this V is 0. Okay. So we have got our virtual short. Does it sound fine, or is there some catch here? There's something I have skipped. What is that? No. The current coming out of this GM should be 0. Okay. Right. It will be, right? Because if this goes on changing, when will this stop? When V is 0. And when V is 0, obviously this current will be equal to that current, right? V is 0 means this current is 0. And again, under DC conditions, that and that will be equal. Okay. So we've got our ideal virtual short, have we? Or is there some catch here? Huh? Why? Why will it not be ideal? Exactly. So now, of course, these GMs will also have their own output resistances. Okay. So that means that V will be some small value, but not necessarily 0. Okay. But it will be better than before. Now we can put our analysis machinery to work and then see what happens. Okay. So this is one more type of op amp, and this is of course quite different from what we had earlier. So maybe let me show the solution properly. So what we wanted here was an integrator so that this control continuously changes based on the error we, okay. Now, of course, how do you make this integrator? We had our single stage op amp, right? Let's say that's the only op amp we knew. So we replaced that with the single stage op amp. Okay. That's what we did, right? This other GM is for just making a variable current source. This is fine. Now, of course, let's say this is not good enough. What do you do next? Compensate. With what? So now you can, this whole thing is a better op amp than before, and you can put that in place of the integrator and so on. You can keep going. Okay. Fine. So let's see what happens. So this is, of course, probably not fair. This is op amp topology is probably not familiar to you. And in fact, it turns out it is not as useful in as wide a context as the other one, the other type of feedback op amp, the Miller op amp that you're familiar with. But for some cases, this is better than the Miller op amp. We'll discuss that briefly. So again, we have, this is just to repeat myself. I have GM1, RO1, and okay. So instead of this, now I have this is a variable current source used to, maybe I should show RO1 here in this case for clarity. So this is RO1, and let me call this is in the second path. This is GM1. Okay. And this is VE. Okay. And let me call this, I don't know, C2 or something. Okay. Now, of course, we have to keep in mind that there will be RO21 here and RO22 there. Okay. That will also be there, right? So this is now an improved op amp, or is it? How do you now quantitatively decide whether it's improved or not? How did we do it for the other op amp? What did we evaluate? Poles? No. I mean, we are still talking about first, let's see, we started with, even with DC input, the first one is giving some error. Now, whether that part has improved, how do we decide? DC gain. Okay. So the DC gain of this is GM1 RO1. What is the DC gain of this? Please evaluate quickly. What is the DC gain of this? Yeah. How would we go about evaluating this? What are you going to evaluate? What is it? Right. So what is that? What resistance do you have at the output? RO1 and RO22 are in parallel, and you want to find out how much current is going through that. And what is the current going through that, or what is the factor? You have one current branch from GM1 and another one from GM22. So it will be GM22, but its input will be GM21, RO21. Okay. So it looks sort of complicated, but you can see the dominant part is this, right? So it is also of the order of GM times RO square. Okay. So basically you get the DC gain of two stages multiplied, right? Just like with the two-stage Miller compensated op-amp, it is similar. Okay. Is this fine? We'll now also discuss the poles intuitively. But before we go there, let's say this gain is not good enough for me. The steady state error is still too large. What should I do? So basically, in place of this integrator, right? This integrator should be replaced by that whole op-amp. Okay. So now you can see how quickly you can generate quiz problems. I have GM1 and this is the integrator that I want to make. Okay. And to make sure that the virtual ground voltage is 0, I have this variable current source. Okay. And now this has to be driven by what? Sorry. And we have, I'm trying to I think this drawing is not very neat. Okay. This is VE. This I can call GM22. And this whole thing is the integrator controlling GM22. Okay. Right. So again, I am sure that you can sit and analyze the poles and zeros of all this. But roughly speaking, what will be the order of the DC gain? Which is the dominant path for the DC gain? The one with 3 stages in cascade, right? So basically this goes through this, gives you one GMRO, another GMRO, another GMRO. So you get GMRO cube and you can keep going. And of course, you know this type of op-amp, that type of op-amp, there is no need to be shy about marrying them together. So you can use that op-amp in this or this one in that. Of course, finally, the point is when you put in all the engineering details, it has to be useful. To generate topologies at the control source level, quite easy. But of course, there has to be some use that you do the analysis, simulations, and find out. But the thing is, it may be, I mean, you can potentially use a Miller op-amp there or vice versa. Okay, the inner part of that Miller op-amp could be this. This type of op-amp is called feed-forward op-amp. Okay. I mean, you can think of this as, if you think of these as two stages which give you the dominant DC gain, you have a stage that is feeding forward directly from the input to the output. So that's why it's called the feed forward op-amp. Okay. So this is now a three-stage feed forward op-amp. Okay. Is this fine? Any questions? And this also, of course, you can do further, like you can go to 4 stages and 5 stages and so on. Again, they will give you essentially like 5 stage means you are getting the gain of 5 cascaded amplifiers roughly. Okay. Now, for the other type of op amp, we intuitively had some criterion, right? That is GM2 by C2 must be more than GM1 by C. That came from the idea that that second op amp must be operational through the unity gain, loop gain frequency that you are trying to achieve. Okay. Now, similarly, with DC wise, we know how it works. Now, the question is, what can you say about this second path compared to the first one? Okay. Again, keep in mind, how did we get this? We said that the main we made a feedback loop using this op amp. We applied DC, let it reach steady state, and after that we basically let the second loop operate and reduce the error further. Okay. So given that explanation, what can you say about this path? Should it be slow or fast, or what is it? Should it be slow? Can it be slow? Should it be fast? What is it? Should be faster? It can be slow, but it can also be fast, or should be slow. Why? Right. No, but what is it that, okay, what was our goal, first of all, in what was not good enough about the first op amp, the one on top? What was the problem? DC steady state error. Okay. And we added the second path to do what? To compensate that. Okay. Now, the way we are doing it is based on the input voltage VE, right? Now, VE will reflect the steady state error only after steady state is reached. Okay. So, this means that this additional parallel path has to be slower, because if you do this while settling, it could be reacting to some other, I mean, not the steady state error. VE, I mean, when steady state has not reached, VE is not 0, right? Then you could have this case of two loops sort of fighting each other and so on. You understand? So, ideally, basically, this should reach steady state, and then you should let the second path come into picture, and then slowly reduce that error to 0. This gives you the intuitive idea that this path must be slower than that one. Okay. Is this fine? And the same here. I mean, these paths must be slower than the main path. Any questions here? So now we can do a bit of analysis. So for that, let's do this. I'll have GM1, but no output resistance. I think I already said this. You can have models with different degrees of sophistication. You should use whatever details are necessary, but not too many, because if you put in every detail into everything, the expressions become so complicated that you won't have any insight. Okay. Because it's not difficult. You can have like the model for everything could be like DC gain plus 10 poles and 5 zeros and so on. But then you can't even write the expressions for it and make any sense. So now when we are not worried about DC, what does it matter if we assume DC gain to be infinity? By omitting this output resistance, that's what I'm doing, right? If I don't have the DC output resistance, if I don't have the output resistance, my DC gain will go to infinity. But if I'm not concerned with DC, when I'm looking for stability criteria, right? Which region am I concerned with? Where the Nyquist plot enters the unit circle. Basically, where the loop gain becomes close to 1. I don't care about DC. DC is like whether the DC gain is 1000 or 10,000, I won't really care. Okay, it doesn't make any difference. So it's easier. So I'll do this. Okay. So what will be the transfer function of the op amp itself? Again, this will be relevant. This will be the loop gain if we have unity feedback loop. So without any ignoring the output resistances, what will be the transfer function of the op amp? GM1 by SC. What about the rest of the stuff? No, it's not ideal. But the capacitor is there, right? What will it be? Please calculate the transfer function. How will you find out? This is similar to finding the DC gain, except instead of output resistances, you have load capacitances. That's all. What form will it be? Again, at the output, we have this capacitor C. So it's basically whatever current is flowing into the capacitor C times the capacitive impedance. Okay, and what is the current flowing into the capacitor C? It is GM1 plus the voltage at the output of the first stage here, that is, what is it? GM21 by SC2 times GM22. Okay, and which can be written as GM1 by SC 1 plus GM21 GM22 by GM1 times SC2, right? Which is of the form omega u by S 1 plus Z1 by S. Okay. So does this ring a bell? This form. Have you analyzed something in this? Assignment, there was a problem like this, right? Okay. And then there was another A of S that was given, which was omega u by S 1 by 1 plus S by P2. Okay. Why did I give that? Yeah. So if you use the other type of two-stage amplifier, actually, again, if you ignore the output conductances, this form will be, of course, it will also have that, which I've ignored. But basically, this analysis, you can look at your own solution to the problem and we can continue the discussion. What did you get, by the way? Just quickly, we'll stop here. But what did you, I mean, did you look at the result of that and result of this? What was the difference? Huh? So P2, where should it be compared to omega u? 1/4. 4. It should be beyond omega u. What about Z1? Below omega u. Basically, that is the intuitive explanation, or rather analytical explanation of this path being slower than that path, right? I said slower. How much slower? That criterion will tell you. Okay. So we'll continue the discussion from there. So there is some. So those you can just look back at the assignment solution and then we can continue the discussion. Okay. So this type of stuff is common with feed-forward op amps. You will have zeros, whereas this one has poles mainly and it has 1 0. Okay.